So far, we've looked at Faraday's law for a single loop of wire in a magnetic field, and we know that the induced EMF is proportional to the rate of change of magnetic flux. However, if we have multiple loops, each loop generates an EMF, so the total will be the EMF of a single loop times the number of loops. So this is the equation we see here. Faraday's law for a coil of n loops of wire. We often use this equation for electric generators. We're going to look now at how a generator works. This animation from PhysClips shows the working of an AC generator, and that is sometimes called an alternator because it produces alternating current. The first thing you can see is that it looks almost identical to the motor animation that you saw earlier, and that's because the parts are almost exactly the same. So every motor, in fact, could work as a generator. If you were to make the loop turn yourself, you would get voltage output. And this generator, if we were to make, instead of that voltmeter there that's measuring the voltage output, if we were to make that a voltage supply, then that would be making this coil turn and it would become a motor. So when it's acting as a generator, what we have to do is make the loop turn by mechanical energy. And it doesn't show what is providing that, but we assume that there is something that is providing the mechanical energy to turn the loop, that is the input energy for this generator, and then the voltage that is getting measured across the two rings, that is the output of this generator. Now, this loop, you can see, instead of having a split ring commutator, this one has got each end of the loop permanently attached to one single ring, and they're there side by side. These are called slip rings, and this slip ring commutator means that whatever is the current in the coil, that is the current going to the output. So there's no switching of the current every half turn. So we're going to look at exactly what is the shape of the voltage or EMF that is going to be generated by this loop as it turns. Now, to begin with, as you can see, the loop is horizontal and the field lines are running vertically. So at the moment, the flux is at a maximum, and maybe you can take a second to think, if the flux is maximum, what should the voltage, which is the rate of change of flux, be to begin with? Now we're going to step it through, and I hope you thought that the voltage should be initially 0, and that now, as the area of the coil that has flux lines through it is decreasing, we have an increasing voltage, and we will get to the point where the loop is vertical. At this point, the actual flux through the loop is 0 because those field lines are running parallel to the loop. But the rate of change of flux is a maximum. And you can see as I step through, you can think of the top and bottom edges of the loop as actually cutting through the field lines that are running vertically. So we step it through, and at the moment, those same edges of the loop are moving still, but they're not cutting through as many lines. So the flux through the loop isn't changing as quickly. Then we get here, and we are now getting to the point where it's cutting through the most field lines, so the flux is changing most rapidly here. Where the flux itself is 0, that gives a maximum voltage. Now you can see that when we have the slip rings, so that we are not changing the connections, they're permanent connections, we have our typical AC voltage curve. And again, you can see the relationship between the circular motion of the loop and the sinusoidal shape of the voltage. And it is going positive and negative because from the loop's point of view, the magnetic field or the magnetic flux is increasing and then decreasing through it from one side and then the other. So it makes the EMF positive one end of the coil and then positive the other end of the coil. So that is the AC voltage. Now, if we just scroll up a sec, we will see that the same generator with one minor change, which is that we've taken away those slip rings and instead put in the split ring commutator. And again, we'll step this through. So at the moment, just like before, the loop is horizontal. That means the flux is a maximum. We hope that means the voltage is 0. And as we start to step through, we see that it was. And now where the flux is dropping to 0, the voltage goes to a maximum. And we're going to step this through because we will see that in a minute it will lose electrical contact, but the loop will keep turning. And by the time it makes contact in the other direction, that means that instead of becoming a negative section of voltage, it remains positive. So it's not a constant voltage, but you can see that it remains positive, and that means the current is always flowing in one direction. So that is our DC generator.